Hey everyone, so the last lecture we discussed about doubly linked list. In this lecture, we will be discussing one more important variation of a linked list known as circular list. So let's get started. So according to the definition, a linked list in which the last node points back to the head instead of null. So in both the variations that we have discussed about linked list till now, either it's singly linked list or a doubly linked list, the last node next pointer is always pointing towards null, right? But in case of a circular linked list, head remains the same, which is the starting node of the linked list, and this is the last node. This is the last node. If it was a regular linked list, if it was a regular singly linked list, this next pointer should be pointing towards null, right? But in case of a circular linked list, it won't be null anymore. Rather, it's pointing towards the head, which is first node, hence giving a circular behavior. That's why the name circular linked list. Okay, and similarly, in case of a doubly circular linked list, and like same as a regular list, we have one more variation in it. Either it can be a singly circular linked list or it can be a doubly circular linked list. In case of a doubly circular linked list, this first will be the head, and let's call it tail, which is the last node. So the head, which is the first pointer, the previous of head is pointing towards the tail, which is the last node, and the next of the tail, which is the last node in the list, is pointing towards the first node. So both back and forth you can move in the circular direction, right? So this is a circular linked list all about. So as I mentioned, it can be either singly circular or it can be doubly circular. It depends upon how you are implementing a circular queue, right? When it comes to parameters, nothing changes. If it is a singly circular linked list, each node will be having data and the next pointer. If it is a doubly circular linked list, then along with the next, there will also be a previous pointer. Hence, the bidirectional nature. And if the head and the tail are pointing towards each other, in that case, it will be bidirectional plus circular, right? Okay, and finally head and tail. So head will always be there, which will tell you that which is the starting node, which is the first node in the list, and tail depends upon implementation to implementation. In some textbooks you will find the tail, which is a pointer to the last node, but in some textbooks the tail is skipped. So it depends upon implementation. All right. So some advantages, some disadvantages that this circular nature brings on the table. Let's talk about advantages first. So when it comes to pros, the first advantage is it is easy to traverse from any node. Due to this circular nature, if I give you a pointer to any random node in the list, you can easily traverse and go back each and every node in a list, no matter you are given a circular singly list or a doubly list. Why? Let's see. Just for the understanding, I'm only taking a singly circular linked list. Okay, this is your head. In case if the list was not circular, then if I need to reach each and every node, I should have the head pointer. If I do not have head, in that case I can't reach all the nodes. At least one of them will be missed. If I had the pointer to, say, suppose this node, in that case, if it is a non-circular linked list, in that case one would be skipped. I can't reach one. If I have pointer to 3, then 1 and 2 will be skipped. I can't reach 1 and 2. But in case of a circular linked list, no matter if I provide you a pointer to any node, due to this circular behavior, if I am at the last node, I can come back to the first one. If I provide you this pointer, let's call it current. If I give you current pointer which is pointed to the third node, then from this third node, you can reach to fourth node. 3 to 4 is possible. 3 to 4, then 4 to 1 is also possible. 3 to 4, then 1, then 2 is also possible. So from 3, you can reach to 4, you can reach to node 1 and you can reach to node 2. Therefore, easy to traverse from any node. From any node, you can reach all the remaining nodes present in the list. Right? So this is an advantage. Second, useful for rotation based problems. So there are certain category of problems that we discussed in the last lecture as well. What if you have to rotate the entire linked list in clockwise direction by k nodes? In that case, in these sort of problems which are based on the rotations and all, the advantage is this circular behavior helps in solving these problems, right? Then, but it also brings some disadvantages or cons, which are implementation is a bit complex. Implementation is a bit complex. Every operation done should ensure that the circular behavior remains intact. And if you are talking about the circular behavior in the doubly linked list, in that case, you need to maintain two circular behaviors. First, the next of the last node and the previous of the first node. Any insertion, deletion at any place, you always have to take care that these circular links should remain intact, right? So therefore a bit complex. Then one more major risk, the risk of infinite loops. If the traversal is not handled with care, the traversal might result into an infinite loop. Why? Because the traversals that we have discussed until now, either it's a singly linked list or a doubly linked list, the termination condition is always like this: while current not equal to null. You start current, you initialize current with head, and in each iteration you increment the current. Current is current dot next. So this is a general scenario to traverse either a singly or a doubly linked list. The termination condition is current should not equal to null. If it is null, I need to search the stop. I reached the end of the list. But this is not the case for circular linked list. There is no node which is pointing towards null in the entire list. So this logic fails. So therefore, if the traversal is not handled with care, it might result into an infinite loop, right? So always take this into consideration. So you have to handle how you search in a circular linked list. All right. Okay, so let's see the first let's now discuss these operations in the circular linked list, starting with the search. As I mentioned just now, it can't be just the termination of the while loop, which is the case the current is not equal to null, because there is no null or none of the node is pointing towards null, right? So how will you stop? Let's take an example to understand this search. You have few nodes. Linked like this, and this is your head. Since you can't terminate the search, you can't terminate the while loop just by condition the current is not equal to null, there would be a slight change. What it will be? You will similar to what if the scenario is you need to find this key. I need to find this key in this list, in this circular list, whether the key is present or not, starting from head, right? If the key is present, then just return true. If it is not, then return false, right? So regular case, you have to start with current, start with head, you initialize the pointer, initially pointing towards your head. Head is anyway given, right? Then if head is null, what if there are no nodes present in the list? In that case, just return false because it's an empty list, a corner condition, the underflow condition, right? Then an infinite loop while true. Then an infinite loop while true. We will check one by one starting from head. Initially current is pointing towards head and I have entered an infinite loop. So if I am entering an infinite loop, I should always add the termination condition before exiting that loop. Okay, what it will be, we'll see. So if the current is pointing towards head, I just need to check the condition whether current's data is equal to key or not. What if, let's assume in this case I am searching for 3, key is 3, I am searching for 3. So this if will check whether current.data is equal to 3 or not. What is the value of current.data? It is 1. It is 1. So it is not. It is not equivalent to 3. So this is not the key, right? If it is not the key, in that case, this won't execute and it will increment the current by next. Update my current. So current will then point to the next node. Current will point to the next node. At this point, line number 7, current is now pointing towards the second node, which is 2, whose value is 2. Now I am exiting the loop, but since it's an infinite loop, I should always take care that there should be a termination condition, otherwise we'll end up in an infinite loop. What it will be? If current is equal to head, this comes the circular behavior. What if I have exhausted my search and I am at 4, then incremented the current by its next? In that case, again after the list is exhausted, the last scenario, if the key is not found, in that case current will anyway incremented and updated to its next. If current is at 4, then it will get updated to head. At this point, I exactly know that I have covered all the nodes, and due to its circular nature, the current is pointing towards head. If the current is pointing towards head, then break the loop. If the current is pointing towards head, then break the loop. Let's see how it works. Okay, but in this case, for our case, we haven't reached the state in which current is again pointing towards head. So for now, I am in the first iteration. I have checked whether the first node's value is my key or not. The answer is no. I have updated current such that now current is pointing towards the second node. And this condition is not true for first iteration. Again, I enter into the loop. We'll check if the data is equal to key. The second check, current.data is equal to 3 or not. The value is 2. At this point, it's 2. So it is not equal. I will update current to 3. Then this if condition, if current is equal to head, answer is no. Head is 1 and current is pointing to 3. So they are not equivalent. So I will enter into the loop third time. At this point, I will check whether current.data is equal to key or not. In the third iteration, current.data, we have found the key, right? This is 3. So they are equivalent. If they are equivalent, just return true. If they are equivalent, just return true. Alright, so we have successfully find the key, end the loop, come out and return. Okay, so this is the scenario in which the key is present. Now what if you're trying to search for, say, 5? What if you're trying to search for a value which is not present in the list? It is also possible. So your code should handle that as well. So in this case, starting with 1, it will compare 1 and 5. They are not equivalent, it will increment. It will update the current. It will compare 2 and 5. The answer is no, they are not equal. Update the current. It will check 3 and 5. They are not equal, it will update the current. It will check 4 and 5. They are also not equivalent, it will update the current. So at this point, now the updated current will again point to its next. So if I am at 4, if I am at 4, if current dot data is 4 or current is pointing towards, if current is just pointing towards the node 4, then current is equal to current dot next. This line will make or will enforce, will update current, and current becomes equal to head for the second time. Why second time? Because we have started with head. We have started with head. So for the second time, current is equal to head. This is the point that we need to check in each while, in each iteration, whether my current is equal to head or not. If at any point current is equal to head, in that case, I have traversed all the nodes and I am about to start traversing the list once again for the second time. That we do not want, because if the list is exhausted, and the current is again pointing towards head, in that case the key is not present. So immediately will break, and once it's break, this will return, false will be returned, which says the key is not present. So at this point, if it is head, then break. This is your termination condition of the infinite while. Okay, it means key is not present. It means key is not present, right? So this is how you will be traversing a value in a circular linked list. There is one more variation in the search, similar kind of, which is rather than just checking whether the key is present or not, the problem can be framed that if the key is present, give the index starting assuming that head is index 0. This is 1, this is 2, this is 3. So you can also maintain a counter, initialize it with 0, and in the while loop increment the counter whenever you find the key. At this point, rather than returning true, you can just return the value of that counter, which is the index of the node which we are searching. Okay. So what is the time complexity? What is the time complexity? In worst case, this will execute, the break will execute, which is the key is not present. So it will be big O of n. The worst case time complexity is big O of n. I might end up searching all the nodes, coming back to the first one and returning false, right? Okay. So now let's see the insert operation in a circular linked list. The first is inserting at the start, inserting at the beginning of the linked list. And this is not that simple when we compare the insertion in the beginning with the singly or a doubly linked list. Let's see with an example. So I'm also adding a comparison with a singly linked list. So what if a singly linked list is given to you with 4 nodes? And this is your head. And similarly, one more linked list is given to you, which is a singly circular linked list. Right? So let's call it list 1 and list 2. List 1 is a singly regular linked list. List 2 is a singly circular linked list. And this is your head. Okay. Now if you want to add a new node at the beginning in case of L1. In case of L1, you need to add a new node X. What do you have to do? We just have to update the next pointer of X such that now it points to the head and head becomes X. We update the next pointer of the new node such that it should point towards my head, and then I will update head to new, right? That's all. So it's a constant time operation. But in case of a circular linked list, you can't just update like this. If you have to add a new node X in a circular linked list, then just updating the next pointer of the new node is not sufficient. Why? Because there is a circular link. The last node is pointing towards 1, which was my head. Now the head is changed. So the last pointer should now point to X, right? For this update, I only have the pointer either to the newly created node or the head. I don't have the pointer to the last node, which is node number 4. So a traversal is required. I need to move the current pointer. I need to take a pointer and move it to 4, which is the last node of the current list, such that I can update this link. This link won't point to the current head. The head is changed. This is no longer head. This is my new head. And this should point to X. This should point to X, right? All right. So let's see how we can ensure this update. Okay. So starting is similar to the one that we discussed. Create a new node. Check if the head is null or not, which is the existing node is empty or not. If it is empty, it is interesting. If it is empty, then the node that you are creating will become the new head. In case of an empty list, if initially head is null, which is the case when the list is empty, then you have to add a new node called X. This is also your head. This should become your new head, and its next pointer should point to itself. New.next is equal to new. Why? Because you are creating a circular linked list. What if the list was initially empty? So the head will be null. If the head is null, the newly created node will be your new head and the only node present in the list. So it is the first and it is the last. So it should also point to its next should point to itself. So this is interesting, right? So ensure this. What if the list is not empty? The regular scenario, there are certain nodes present. In this example, we have taken 5 nodes. You take a pointer current. Which is your head, initialize it to head. So the current, this was your head, and now this becomes your current pointer. Initially current is head. A while loop. Why a while loop? You need to reach to the last node. Why? Because you need to update. We have to update the next pointer of the last node in such a manner that it should now point to the newly created node, not the existing head. Why? Because we need to add a new element at the beginning. So my head will change. So everything which is pointing to the previous head should also get updated. So the while loop, while current's next not equal to head. So this condition is sufficient to identify that whether I have reached to the end or not. If this is not the case, then just update the current to next. Initially current is pointing towards head. So current's next is head or not? Answer is no, it is not. Update current. Now check whether current's next, which is 3, is pointing towards head. Answer is no, update it. Now check, answer is no, update it. At this point, the current link, currently we haven't linked anything. Head is my 1, and yeah, this is the state of the list. At this point, when the current is pointing to node number 4, is this condition true? Current's next is not equal to head. Is this true? Answer is no. The current's next is pointing towards head. So not equal to will become false. Not equal to will become false. Why? Because current's next is head. So therefore the while will terminate. The while will terminate. This will exactly give me, this will ensure that the current pointer points to the last node. Then only its next will equal to head. Right? Easy? Okay. Now what if I have reached to the end? I have reached the last node. Now I need to have two updates. I need to update two pointers. The first is the new node. This is my new. I have to link my next pointer of the new node to the head, current head, existing head. Then I have to update my current's next so that it should point to new, and then new will become my new head. Let's see. First operation, line number 8. Current's next is equal to new. Current's next is equal to new. What I am doing? I am removing this link. And updating current's next such that it should point to new. Current's next is pointing towards new, line number 8. This link okay. So this current's next will become my new. Clear? So I have created a circular pattern. Now to complete the circle, news next should also point to head. This is the next operation. News next is now head. News next is now head. This is my line 9. This is my line 9. Okay. Then the last, which is I have to update the head. Line number 10. Head becomes new. So this is no longer head. This is my new head. Update the head. Right? That's all. Just return head. You have successfully added a new node whose value is x at the beginning of the list. Three major operations. Go to the last node, update its next to point to the new node that you have added, update the next pointer of the new node to head, and then finally update the head. Right? So what should be the time complexity of inserting an element in the beginning of a circular linked list? The answer is big O of n. Why? Because there is a while loop. Which is responsible to reach to the last node. We are traversing the entire list to add a new element in the beginning such that the circular behavior remains intact. So do not get confused between the time complexity of insertion at the beginning in case of a circular linked list when compared to insertion at beginning in a singly or a doubly linked list. In both the cases, in singly and in doubly, insertion at beginning is a constant time operation, big O of 1, but this is not the case for circular linked list. It is big O of n. So do remember it. Okay. Then our homework. What if you have to insert at the end? Think about it and come up with a time complexity. What if you have to insert at the end? This is also similar to inserting at the beginning. It's just you have to add a new node at the end, update the current ends pointer to the new node, and the next pointer of the newly created node should point to the head. Head remains the same. That's it. And this will also be a big O of n operation. You have to reach to the last node. Okay. Next one. Insert after a given node. So again, a key is given to you. Let's understand it using an example. Let's suppose you can take one more, 5 nodes. We have 5 nodes in a singly circular linked list, and I am not discussing about these operations in case of a doubly linked list. Like, it will unnecessarily increase the complexity of the circular linked lists. Okay, so based on what we discussed in doubly linked list, all these operations and what we are discussing now, you can combine and come up with an approach in order to have any operation in a doubly circular linked list. Okay, so this is my head. I need to insert x. I need to insert x after key. Say, let's assume after 3. So key is 3, and let's assume x is 6. I need to add a new node whose value is 6 after 3. So the after update, the list should look like this: 1, 2, 3, 6, 4, 5. This should point to 1. It should look like this. Okay, this is after update. Cool. So let's see, and the idea remains the same. You just have to add a new node such that the circular behavior remains intact. The first scenario, check for underflow, which is if it's empty, so the key is not found, return it. Next, take a pointer current, start with head. Take a pointer current, start with head. Initialize the current pointer with head. Then a infinite loop while true. Check for whether current's data is key or not. You need to stop exactly at the point where the data of current is matching with your key, which is 3, because we need to insert the new node after the key is present. Okay, just immediately after the node whose value is matching with the key. So idea remains the same. I need to update my current until the key is found. If current.data is key, if key is found, in that case this if block will execute, else I just update the current. So until key is not found, I will keep on updating my current. So key initially it's 1 is not equal to 3, so I will update the current. Again 2 is not equal to 3, which is the key, I will update the current. At this point, the if condition becomes true. This if becomes true, current.data is equal to key. I am exactly at the node after which I have to insert my new node, right? So if I have found the key. Okay, so now the next step is to insert after this current. So new becomes, this initialization can also done like before the while, but it's fine if we are like declaring the new node in this if as well. Okay, a new node is declared with value x is 6. So a new node is declared with value 6, right? News next is equal to current.next. Current is 3. News next is equal to current next. News next is equal to current next. What I've done? New.next is equal to current.next. This is, let's call it link number 1. Okay. Next, current.next is equal to new. Current.next is equal to new. remove this pointer such that the current is no longer point to the to 4. It should point to the new node that we want to add, right? So this currents next is new. This is new. Let's call it link 2. So current next is now updated to 2. This is link 2, right? So this is the regular insertion, right? Then return head, then return head. Just return head. You do not have to do anything. Return head. Why? Because head remains the same. Head remains the same, right? So then if current is head, then key is not found. So like this is the scenario in which 3 is not present in the list. Okay. So that's how you will be adding a element. You will be inserting a key. You will be inserting a node after a specific key. In worst case scenario, what will be the time complexity? Similar to the other insertions, big O of n, right? The worst case time complexity will be big O of n. What if I need to add the element after 5? I have to add the element after 5. Okay, so now I need to ask you one thing. What if the key is 5? What if the question is, you have to think about it. The question is, what if key is 5, which is I need to insert an element after 5. This is same as I need to insert at the end of the list. Will this logic work? Will this logic work? Think about it. Will the current logic, will this logic work? And the meaning of this question is, should we need to do something else in order to maintain the circular behavior of the list or not? Okay, think about it, and yeah, just think about these questions in order to make the logic, make the code clear to you and understand it in a better way. Okay, all right. So next operation in circular linked list will be deletion. Let's see how we can delete an element at the start of the list. So this is also similar to how we discussed insertion at the beginning. The only difference is once the head is deleted, you have to ensure that the second node becomes your new head and the last node should point to the newly appointed head. That's it. Okay. So let's have an example. Let's assume there are 5 nodes chained in a linear fashion and this is the head, right? What we are discussing, we are trying to remove the first node, which is head, from the linked list, deleting the first element or the first node. Okay, so you have to pass head. There won't be any x over here. Why? Because we are trying to delete the first node, which is head. So you can ignore it. Okay. First scenario, what if the head is null? The underflow state. What if the head is null? Underflow state, just return the error. Second scenario, what if there is only one node present in the list? How will you identify? I mentioned this earlier as well. While inserting, if initially the list is empty, in that case you have to create a new node and then make it as head, and the next pointer should set to itself. So what if there is only one node that we are trying to delete? this is an underflow or empty list, right? The second scenario, only one node. In case of a single node, it will look like this. It will look like this. Let's assume it's having value x. This will be head and it will point to itself. So how to identify that in a circular linked list there is only one node? Head dot next will be equal to head. Heads next should be equal to head. Okay. So if this is the case, we are sure that there is only one node in the linked list. Just free it out and return null. Delete it and return. Free it from the memory and return null. Okay. Because this is what we have to delete. We have to get rid of head. In case of a single element or single node, there won't be any nodes available. So we'll return null. Okay. Else, the regular scenario. What if there are certain elements already present in the list? Idea will be the same. You have to update the pointer of the last node such that it should point to the new head, which is the second node, once you successfully remove the current head. Okay. For that you need to reach to the last node. For that, to update this link next of the last node, which is 5, we have to first reach to the last node. This is what we'll do. Initialize a pointer with the name last with head. You can take like any name, current will also work. So let's have a pointer which is initially pointing towards head. So I will keep on increasing, I will keep on moving it towards its right until last dot next is equal to head, which will ensure that I am pointing to the last node. While last dot next is not equal to head, I'll keep on updating last. Correct? This is simple. We have already seen this logic. I will keep on updating till my last dot next is not equal to head. In this case, last dot next would be pointing towards 3. So I will update. Now last dot next will point to 4. So again I will update. In this case, last dot next is pointing towards the last node. Still I will be updating. And finally, when the pointer last is pointing to the last node, the actual last node, in that case last dot next would equal to head. So it's where I will stop. So this while will ensure that the last should point to, this will ensure that last pointer should point to the last node of the list. Right? It's like logically correct as well. I need to reach the last node in order to update its next pointer. So the next thing that we will be doing is I will update it. Last dot next is equal to head dot next. I will update it in such a way that it should point to head dot next, which is the immediate second node, which is the second node in the list. What I have done, I have removed this link. This will be removed, and this next will point to, the next will point to 2, the next will point to heads next, the next will point to heads next, right? So line number 9, this is line number 9. This link will be updated in line number 9. Alright. So once I have successfully updated, or I have added the circular behavior based on my operation that I'm trying to do, which is deleting the first element, I can get rid of this head. And appoint the new head. 2 should be my new head. Okay. So just take a temporary pointer. Take temp. Temp is equal to head. Update your head. take temp, point it towards head, update your head such that head is equal to head.next, head is equal to head.next, and then remove temp, free temp, get rid of temp, right? So free temp will remove the previous head before updating, because we have already stored the reference, right? And then just return the head. So by this you have successfully deleted the first element, and you have ensured that we have ensured that the circular behavior remains as it is. Now the new head is 2, 2, 3, 4, 5, then again 2 is linked in a circular fashion. Alright. So this is how you will be removing the first element in the list. And what will be the time complexity in worst case? Or like this is the same. So if you are removing from start, there is no worst or best. You always have to do this operation. So the time complexity would be big O of n. Why? Because line number 7 and 8, the while loop will keep on executing. The number of iteration of the while loop at line number 7 will be 9. Not 9, will be n based on the number of elements. We are trying to reach to the last node in order to update the circular pointer. Okay. Now for you, if you have understood it, then two scenarios in homework: deleting the last element and deleting by key. Deleting the last element, what if I want to delete 5, which is the last element? What if I want to delete 3, which is in between, somewhere from in between beginning and the end? Okay, so think about it and come up with an approach in order to perform these two operations. So this is your homework. Alright, so now let's discuss another important algorithm when it comes to circular queues. The next algorithm is known as Floyd's algorithm, and this is an important algorithm which is used to detect cycles in a chained list. What if a linked list is given to you and there is a cycle present? It can also be used to identify whether a linked list is circular or not, but the idea is to detect a cycle present in the list. Okay, so circular linked lists are cyclic in nature, but all cyclic lists won't be circular in nature. There is a difference. Okay, so let's see how exactly the algorithm is framed, and then we will see how to detect the cycle in the list. For example, a list is given to you. So this is a regular singly circular list in which the last node is pointing towards the first. This is your head. 1, 2, 3, 4, 5. So this algorithm will be able to detect that there is a cycle. There is, right? 5, the next of 5 is pointing towards 1. There can be other scenarios for cycles. What if a similar chain of 5 nodes is given, and rather than pointing the last next to head, what if it is pointing towards the third node? So there is a cycle present, right? But the next of the last node is not pointing towards head. It is pointing to some other node, but there is a cycle. In this case, cycle is 3, 4, 5 and again 3. So this is the cycle. This is the cycle. In this case, the entire chain is cyclic. This case, entire chain is cyclic. Okay. So this algorithm will help you to detect whether there is a cycle present or not. Let me draw it. Yeah, so this is the cycle. In this case, the cycle is there, but only 3 nodes are covered in the cycle. Okay, so let's see how the algorithm works. Okay, so the idea is very simple. We have to maintain 2 pointers. Let us call them slow and fast. The first pointer is called slow and the second pointer is called fast, and we have initialized both of them by head. Initialized both by head. Okay, so we will understand this algorithm with a dry run or with an example. Okay, let's assume for first example there are 3 nodes. So the nodes can be odd or even. Okay, there are only 2 possibilities. This is L1, this is L2. One, two, three. 1 is connected to 2, then 3, then 3 is again pointed towards head. This case, there are 4 nodes. 1, 2, 3, 4, and the next of 4 is pointed to 1. Okay, so we have taken 2 examples. Let's see them one by one, that how this algorithm works in order to detect the cycle. So we have taken 2 pointers. Let me move it. Alright, so initially take 2 pointers, slow and fast. I am calling them S and F. Okay, so both S and F are pointing to head. Both S and F are pointing to head. Right, line number 1 and 2 will ensure that both the pointers should point to head. Then we have a while loop, while fast not equal to null and fast dot next not equal to null. There are 2 conditions for the while loop. My second pointer, which is fast, why it is called fast, we'll see. So fast should not equal to null and its next also should not equal to null. Okay, if this holds, then I will update my slow to point to the immediate next, and I will update my fast by 2 steps. The slow pointer is updated by a single step, which is the scenario that we usually have in order to perform any operation in a linked list. We take a current pointer and keep on updating it by a single step. In this case, slow will be your current, and there is one more pointer which is we are updating that by 2 steps. So move slow by 1, that's why it's called slow. Its movement is slower compared to the faster one, and move fast by 2. Okay, and we will keep on doing this until the termination condition of the while loop is there. Alright, so for instance, f.next is 2, which is not null, and f.next.next is also not null. So we can update both of them. So slow will get updated by 1 step and fast will get updated by 2 steps. Fast will be is equal to fast.next.next, fast.next.next. So after first iteration, slow will be pointing towards the second node, and fast pointer will point to the third node. Okay, now again, this condition is the important one. This will ensure that the cycle is detected successfully or not. If at any point in this while loop my slow and fast becomes equal, the slow and fast pointer will be equivalent at the start. Both are pointing towards head. So the idea is we are starting with the same node and we are incrementing slow pointer by 1 step and we are incrementing the fast pointer by 2 steps. Okay, so the space of the fast pointer is double compared to the slower one, right? So if there is cycle, there will be a point when both slow and fast pointer again will meet before the slow pointer reaches the end. Slow pointer will be somewhere between. Why? Because let's assume there are n nodes. Right? At exactly n by 2 steps. My slow pointer has moved to n by 2th node. my slow pointer has moved to n by 2th node, right? But the fast node is moving twice the pace of the slow node. So after n by 2 steps, the fast will be at nth node, right? So when slow pointer is exactly somewhere in the middle, the fast will point to the last node, right? And similarly, after again n by 2 steps, if the cycle is in such a way that the last node is pointing to the first node, where all the nodes are present in the cycle, in that case, after n steps, both slow and fast pointer will meet. Why? Because, let me explain. This is after n by 2 steps. Okay, after first n by 2 steps, slow will be somewhere in between. After n by 2 steps, both pointers started with this. The slow pointer is incrementing by 1 and the fast pointer is incrementing by 2. After n by 2 steps, slow will be somewhere here, okay, in the mid, and the fast will be at the end, right? Then after again n by 2 steps, after again n by 2 steps, slow will be somewhere at the end, right? And the fast pointer will again complete one more cycle. So the idea is, till the slow pointer completes one cycle, the fast pointer should complete 2 cycles, and there should be a junction point where both these 2 pointers will meet, apart from the initial state where we have started both of them at the same point. Okay, and after next n by 2 steps, slow will complete one cycle, and fast will complete 2 cycles, right? And exactly after n by 2 steps, they will meet again. They will meet again. Understood? Logical only, right? We are updating the slow pointer by 1 step and we are updating the fast pointer by 2 steps. So there will be a scenario after exactly n iterations. If the loop has n nodes, after n iterations, both these pointers will meet again. Why? Because fast pointer will be able to complete 2 cycles. Till the slow pointer has completed one, and the junction point will be same for both the pointers. So there will be a scenario in which slow and fast will become equivalent only if there is a cycle present. If there is no cycle, then it is not possible, and your while loop will terminate either by this condition or by this condition, right? Okay, so we are like, let's go again to list L1, which is first example. After first iteration, S is pointing towards 2 and fast is pointing towards 3, right? We'll check whether this slow and fast is equal. No. Again, we'll get into the loop. Since there is a cycle, so neither fast will be null nor fast dot next will be null. No pointer will be null. Why? Because there is a cycle present. So again, we'll update the slow. We'll update the slow by 1 step, and we'll update the fast by 2 steps. So first step is head, and then this. So this will be your fast after second iteration. Right? Again, fast and slow are not equivalent. Slow is pointing towards 3, fast is pointing towards 2. So we'll get into the loop again. Update slow. So slow will get updated to this 1, right? And fast will get again updated to 1 at this point. Why? Because fast is 2. 2 dot next. So fast will again update to head. So if you have a cycle with 3 nodes, exactly after 3 iterations, both fast and slow met at the same node, which is head. This will be the termination condition if the cycle exists. Slow is equivalent to fast, return true. We have detected the cycle. Slow and fast both are pointing towards head, and exactly after 3 iterations, because there are 3 nodes involved in this cycle, right? So this was the point that I am trying to explain. After n/2 steps, slow will be somewhere in between, but fast will complete. The fast will complete the traversal. It will be at the last node. Then when next n/2 nodes, after n/2 next iterations, the slow will be either through the last node or the first node, and fast will also be at the same node. That's where they will meet again and the loop terminates. The cycle is detected successfully, right? Or else if there is no cycle. Let's see one more example. If there is no cycle present, what if 1, 2, 3, 4, null. Let's call it L3. L3 is the case when there is no cycle. So we are validating whether it works correctly or not if the cycle is not present. So it should return false if there is no cycle. This is head and this is fast and slow. Both are pointing towards head, right? So we are updating the head. Slow will be updated by 1 step. This will be slow and this will be fast, right? After second iteration, this will be slow and this will be fast. So after 2 iteration, fast will equal to null. So therefore the while loop terminates. Fast should not equal to null, but fast is null in case there is no cycle. So first condition, if you see it closely or like carefully, there are 2 conditions involved in the while loop. So this will ensure that while should terminate in case there are even nodes. Terminate for even nodes, and both are scenarios for the list having no cycle, and this will be the case of termination for odd nodes. Fast.next will be equal to null. Why? Because if the nodes are odd, what if there is one more node 5? In that case f should point to 5, so f.next would be null because 5 would be the last node which is pointing to null, right? So for odd nodes this will become the termination condition, for even nodes this will become the termination condition in case of a chain, with no cycles, right? So L2 you can think on your own. This will also detect the cycle. There will be a point when both S and F will meet, so you can try it in homework. Alright, so that's all about Floyd's algorithm. So what will be the time complexity of this algorithm? What will be the time complexity? The slow pointer is completing one entire iteration. So worst case complexity is the last node is pointing to the first one. It will be big O of n. So you have successfully detected a cycle in a chain in big O of n time, right? Okay. Alright, so there are a few more practice problems on circular linked list. So let's go through them and we will be seeing few of them in the demo. But yeah, first have a basic overview in a broader way of these problems. And like these are important problems, not only from the gates perspective, but also from the interviews perspective. Alright. First one is find the nodes where the cycle begins. So you have seen the cycle detection algorithm, the Floyd's algorithm. Now I want the node, I want the exact node, I want the pointer of the node from where the cycle begins. For instance, there is 1, 2, 3, 4 and then it is linked again with 3. So you need to give me the pointer of this node 3 from where the cycle begins. Cycle begins at node 3, right? So come up with an algorithm, think of a logic that should return me the pointer to the node from where the cycle starts, right? Then there is one more variation. give me the number of nodes in the cycle. Give me the number of nodes in the cycle. So this is basically starting three problems. First, 1, 2 and 3 are variations in Floyd's algorithm. If you know how to detect the cycle, you can easily figure it out. Problem number 1, 2 and 3. The third is remove the cycle from the list. You have to remove the link. How will you remove the cycle? You have to remove the link which is causing the cycle. In this case, 4 to 3 is the link that you need to get rid of in order to eliminate the cycle, right? And for second one, the answer would be 2 for this example. It should, your logic, your code should return 2. There are 2 nodes in the cycle, right? Okay. Then the next, splitting a circular linked list into 2 halves based on the slow and fast pointer that we discussed exactly from the middle. So either there will be even nodes or odd nodes. What if this is how the list looks? So it should give me 2 lists. First, it should, like, this is your head. The code should return me 2 heads, the pointer to 2 heads, h1 and h2, where the first list is like this and second is like this. This is my h1 and this is my h2. In case of even nodes, in case of odd nodes, h1, the first link can have like n plus 1 by 2 nodes and the second can have n minus 1 by 2 nodes, right? Okay. Then the next one, merge 2 circular linked list to 1. Merge 2, this is opposite, exactly opposite of 4. I will give you 2 head pointers. h1 and h2 are given to you. You have to return a pointer to a linked list which is a circular linked list combining both linked list L1 and L2. That's it, right? Just opposite of problem 4. Then next, insert a new node so that the list remains sorted. Insert a node in such a way that the circular linked list remains sorted. This you can revisit once we discuss sorting. Okay. Then 7th is important. 7th is important. I won't be discussing it over here. Joseph's problem. Given n people in a circle, eliminate every kth unit until one survives. So think about this problem and try to come up with a solution, right? And it is the people are, you can treat of people as nodes and the nodes are linked in a circle, right? So it is the problem based on circular linked list. The last 3 or 4 problems are a bit complex one or the miscellaneous or advanced problems. Then 8th, reverse a circular linked list in place. So this is not that difficult. You can easily reverse a linked list, circular linked list. So if the list is like this: 1, 2, 3. This is your head. Then after reversing, it should be 3, 2, 1, and 1 should point to 3. This should be your new head. So this is reversing a circular linked list is, right? Then rotating a circular linked list by k, keeping it circular. This is not that difficult problem. 9th one, rotating a list. Rotating a list in either clockwise or in counterclockwise direction is just updating the head pointer. Why? Because this is a circular linked list. This is a circular linked list. So you have to update the head pointer by k units. Head pointer by k units towards the next direction in case you are trying to moving it in counterclockwise. But in case of a clockwise, you need to move it. You need to move the k pointer to n minus k steps. Okay. So think about this problem and come up with a solution. This is not that difficult. The last, remove duplicates from an unsorted list. This problem can also be framed for sorted as well. So whether the circular linked list is given to you, whether it is sorted or unsorted, remove duplicates. Okay. So come up with an algorithm, and few of them we will be discussing in demo. All right. Now let's implement the cycle detection. So what if the linked list is provided, a head is given to you, and you need to detect whether there exists a cycle in the list or not. Okay. So which is also known as Floyd's algorithm of cycle detection. Okay, so as we have discussed this algorithm in the class, so let's use the same linked list. Then we will tweak this list in order to change the cycle to see whether the algorithm works or not. Okay, so let's create a function cycle detection, which will take the head pointer. Let me define a temporary node as current, initially pointing to the head. Now in this case, the algorithm says we need to maintain two pointers. We need to maintain two pointers. This is our existing list, right? It is node 1 pointing to 2, then 3 is pointing to 4, and again 4 is pointing towards 1, and this is my head, right? So we will take two pointers, fast and slow. Both are initially pointing to my head, right? This is my slow pointer and this is my fast pointer, and we increment these pointers in such a way that every iteration updates the fast pointer by 2 jumps and the slow pointer by a single jump. So after first iteration, slow will be pointing towards the second node, but fast will be updated with twice the pace of the slow node. It will be like this. Okay, then in the second iteration, slow will again be updated with a next, and the fast will update it to next, which is twice the speed of the slow. This, after second iteration, this will be the scenario. Then slow will update again and it will point to the last node, and fast will be updated to point to the second last node. And after the next iteration, again slow points back to, due to the cyclic behavior, again slow will point to my head. This will be my slow after 4 iterations, and fast will also be pointing to my head. So if there is a cycle, then both these pointers will definitely meet in such a manner that there will be one complete cycle. The slow pointer will be like will have completed one cycle, and the fast pointer will, like at that point when these two pointers are meeting again, fast will be like there will be two complete cycles for the fast pointer, but they will definitely meet. They will meet. Right? Okay. And like if there are no cycles, in that case, either the fast or fast next will definitely be null. If in this case the next or the 4 was null, in that case you, like when the slow will be halfway around, the fast will reach to the termination or the last node. So there will be like two scenarios: either fast becomes none or fast next will become none, based on even or odd number of nodes in the list. Okay, all right. So this is the overall algorithm, and yes, this algorithm is like linear time algorithm. The time complexity will be big of n. Why? Because slow pointer is completing a complete cycle. In worst case, the last node will be pointing towards the first one, where the cycle contains all the nodes present in the list. So in worst case scenario, the algorithm might have to traverse the entire cycle, the slow pointer, right? Okay, so we do not need a current pointer, so it's not required. We just need two pointers, slow and fast, where both are initialized with head, right? Okay, so the while loop, which will be true When f is true, which is f is not null, the fast pointer is not none, and its next is also none. If both are true, then only we keep on updating the fast and the slow pointer in search of in hope of, like, with a hope that these two pointers will meet, right? So the step count for slow will be 1 and step count for fast would be 2, right? Then the check if s is equal to f or not. If it is, just return true. We detected a cycle. Or else, if we come out of this while either by this condition or this condition, just return false. Okay. All right. So let's call this function with head of, yeah, this cyclic list 1 2 3 4 again 1. Yeah, so it is returning true. Let's remove the link which was creating a cycle. Now it's like this is not executing, head again is not executing, so there is no cycle. The next of 4 is null. Yeah, it's false. So it's working as per the expectation. So that's how you will be detecting cycles present in the list, right? And this is also known as Floyd's cycle detection algorithm. All right.